So my name is Saurabh Kadekodi, and I'm here to convince you why your storage systems gotta have heart. And this is joint work with my advisors, Rashmi Vinayak and Greg Ganger. So this work is about tailoring redundancy according to disk failure rate heterogeneity in cluster storage systems in order to reduce storage cost. So to put things into perspective, by cluster storage systems, I mean any storage subsystem of a distributed system, which typically consists of thousands to millions of disks, and which is usually built incrementally in response to demand. So what happens as a result is that your disk fleet ends up being a heterogeneous collection of disks, heterogeneous in terms of reliability, which might be due to buying disks from different manufacturers because of differences in vibration and temperature experiences, I/O churn, and so on. So this is the one slide overview of the talk. Data redundancy, in order to protect against disk failures, typically is designed as a one scheme for all across your disk fleet. The reality, unfortunately, is that different disks tend to fail differently, even from a single storage tier. And the key idea of this work is to explicitly consider reliability heterogeneity in deciding the redundancy of the data being stored on particular groups of disks. To do that in a systematic way, we have designed and developed HeART, the Heterogeneity-Aware Redundancy Tuner, which tailors redundancy according to disk failure rate heterogeneity. It's a safe, accurate, and online framework. All these three properties are key, and I'll explain them in later slides. And the result is that it has lower storage overhead and therefore reduced storage cost. So we evaluated HeART on a production data set, and we could save anywhere between 11 to 33% disk space. So at today's scales, failures are common, and the most common way to protect against failures is by having redundancy of some sort. Now, disk failures are typically measured in terms of annualized failure rate, which is the expected percentage of disk failures in a given year. The most popular fault tolerance schemes could either be full data replication or erasure coding. And the key point is, the key takeaway is that today, redundancy configurations tend to ignore the failure rate differences of the underlying disk subsystems. So how much are these failure rate differences? So we evaluated the Backblaze dataset, which has over 100,000 drives and has over 5+ years of reliability. And on this graph, the x-axis shows the different disk groups by grouping the disks in terms of make and model. And on the y-axis, we have the annualized failure rate in terms of percentage. So the difference between the strongest and the weakest disk is over 3 times. And the key point is that along with that, no two different disk groups have equal amount of failure rate. This has been shown to be true in SSDs as well in a FAST 2016 publication. And so no single redundancy scheme can actually turn out to be optimal for disks that fail differently. So what would usually happen is that a conservative redundancy scheme would be chosen according to the weakest disk group, which means that the disk data on the stronger disks is overprotected. And if the redundancy schemes are not designed carefully, what would happen is you might choose a certain redundancy scheme for which some disk group might have a higher failure rate and therefore might possibly risk data loss. So the right way we think to go about this solution is to actually inform the redundancy layer about the differences in the failure rates among the different disk groups. The challenges to do this are that the disk failure data has to be monitored on the fly in the field. The spec sheet failure rates are very different from what ends up happening in the field. Moreover, a disk's failure rate varies over its lifetime. So these are the two main challenges in having a redundancy tuning mechanism. Therefore, any redundancy tailoring scheme has to have the following properties. It should be safe, meaning that whichever reliability phase of life the disk is in, it should never risk data loss. Secondly, we should be accurately identifying the different phases of life because we're going to change redundancy in the different phases of life. Finally, this technique has to be online. And by online, I mean real time, which means that if you're in a particular phase of life and you realize that there was a phase of reliability phase of life in the past where you could have optimized redundancy, that opportunity is lost. So you can only act on the reliability phase of life that you are currently in. So let's look at how a disk failure rate varies over its lifetime. So for a particular disk group, the disk failure rate can be represented as a bathtub curve or the hazard curve, where you have the age of the disk on the x-axis and the failure rate on the y-axis. So when the disks are initially installed, you have the infant mortality or the burn-in period, where you have a high failure rate. This is followed by a low, stable, useful life failure rate. And finally, you have the wear out, where again the failure rate increases. For the dataset that we analyzed, the infancy lasts anywhere between 3 to 5 months, and the useful life lasts anywhere between 3 to 4 years. And the key idea is that we identify when useful life begins, and we change the redundancy to have a lower redundancy during useful life because the failure rate is lower, which results in lower storage cost. Now, like I mentioned before, a typical cluster storage system is made up of multiple disk groups, which means you have to monitor different disk groups simultaneously, and they go through their different phases of life at different points in time. So we propose that for every disk group, no matter, even if it has a bathtub curve different from another disk group, there is some default redundancy scheme that is deemed good enough without our optimization. We call that redundancy scheme FT default. And we propose that FT default be used during the infancy and the wear out of each disk group, because during those times, the failure rate is high. And for every disk group's useful life, we propose having a disk group specific fault tolerance scheme, in this case, FTX and FTY, for disk groups X and Y. Okay? So abstracting this timeline, we have default fault tolerance schemes on either ends of a disk group's lifetime, and a disk group specific fault tolerance scheme during its useful life. And we want to answer a bunch of interesting questions about this timeline. One is, how do we detect when infancy ends or when wear out begins? Secondly, is the AFR during the useful life low, stable, and well behaved? And finally, what should the redundancy be during a disk group's useful life? And to answer these questions in a systematic manner, we have developed HeART, or Heterogeneity-Aware Redundancy Tuner, which takes as input a target reliability requirement in terms of mean time to data loss. It's a time measure. This is the standard reliability metric. And the periodic disk health monitoring data, which is expected to be a part of any sizable cluster. HeART is made up of 3 modules, an anomaly detector, a change point detector, and a redundancy tuner. And these 3 modules will help us answer those 3 questions. So let's look at the first question of whether the AFR during useful life is low and well behaved. So typically, during useful life, the failure rate is actually flat and is within a certain reasonable confidence level from its mean. But there could be factors external to the disk's characteristics themselves that might cause simultaneous bulk failures. For example, someone knocks the power off of a rack, there could be accidents or human error, and so on. So these simultaneous bulk failures increase the failure rate, and if that happens during useful life, this increased failure rate can appear like a premature wear out. And we deem these external failures as anomalous failures. Now, our benefits of HeART are proportional to the length of useful life. And so we'd like to make sure that if a failure rate increase happens, it's due to the disks themselves and not due to external factors. So let me show you an example. So this is the bathtub curve of disk group H4B from the dataset we analyzed. And immediately you can observe that there are these vertical spikes, which are not characteristic of a typical bathtub curve. And these are possibly due to simultaneous bulk failures that happened during the disk's lifetime. Now, this clearly indicates that we need to have an anomaly detector as a part of HeART. So we took an off-the-shelf anomaly detector and ran the data of this bathtub curve through it. And it pointed out points A, B, C, D, and E as anomalous. And when we filtered out the disks belonging to those particular points, the resultant is the black curve, which is indeed flat and well behaved during its useful life. So points A and B, for example, were caused because of more than 300 disks failing at the same time. So this shows that an anomaly detector is an essential part of our framework. So the next question of how do we detect when infancy ends and when wear out begins? So we want to accurately identify the knee of the curve because we're going to change the redundancy during useful life. So let's look at what happens if we miss that. So if we are too hasty in declaring end of infancy or too lax in declaring a start of wear out, we might actually miss our reliability target because our redundancy has been lowered during useful life. Similarly, if we are too lax in declaring end of infancy or too hasty in declaring wear out, we are going to rid ourselves of the benefits possible. So we employ online change point detection algorithms to correctly identify the knee of the curve. So for both anomaly detection and online change point detection, we leverage existing state-of-the-art algorithms. For anomaly detection, we use the robust random cut forest algorithm. And for change point detection, we use an algorithm called ruptures, which has a sliding window-based approach, where there are two adjacent sliding windows, and when the original signal is different in the different sliding windows, a knee of the curve is said to have reached. So the length of the window we choose as 30-day worth of reliability data because a 15-day or a weekly reliability data was too jumpy and not indicative of the natural trend of reliability. So to answer the final question, what should the redundancy be during a disk group's useful life? So this question has a data-driven answer. So I'll go through our evaluation, which will answer this question. So again, going back to the data set we analyzed the Backblaze dataset. It belongs to a backup company, more than 100,000 disks, and it has 5+ years of reliability. For our analysis, we analyzed 6 makes and models from this disk fleet, which had statistically significant number of disks. By that, I mean roughly 10,000 or more disks. And the nomenclature is as follows. So if you look at the column on the left, the letter represents the make, the number represents the size in terabytes, and the letter to the right represents the model. So H4A and H4B are 4 terabyte disks belonging to the same manufacturer, but different models. And if you look at the age, the disk ages vary anywhere between half a year to over 5 years. Okay. So from among these 6 disk groups, I'm going to I'll first talk about the methodology of how we evaluate costs, and then I'll go to the graphs. So this is a slightly busy slide, so bear with me. So like I mentioned before, HeART requires a target reliability to be provided in terms of mean time to data loss. Now, mean time to data loss is a time measure. So higher the MTTDL, the more resilient the data is. So a reliability target can be provided by a storage administrator in an absolute sense, or in the absence of which, we take the highest failing disk group and our default fault tolerance scheme, the FT default that I mentioned before. The default fault tolerance scheme, when applied on the highest failing disk group, results in an MTTDL value. That is the lower bound on the tolerable MTTDL across the disk fleet. And we keep that as our target MTTDL. So disk groups that have a lower failure rate have a higher MTTDL, so they're naturally more okay. So for other disk groups, other than the highest failing disk group, we find an alternate disk group that meets our target, alternate redundancy scheme that meets our target MTTDL, and at the same time, a redundancy scheme that is cheaper. And by cheaper, I mean it has a higher ratio of data blocks to parity blocks in a given stripe. So we restrict our search for alternate redundancy schemes by having the following 2 constraints. One is that any alternate redundancy scheme we choose has to tolerate at least as many failures as the default fault tolerance scheme. And secondly, we need to have some sort of a reasonable upper bound on the maximum width of the alternate redundancy scheme. It's because the wider we go, it has an impact on the reconstruction cost. And because we have to touch more disks in order to reconstruct, we might end up hitting slower disks and the straggler problem, and therefore will be only as fast as the slowest disk. Okay, so on our data set, S4 disks had the highest failure rate, 4.01%. And therefore, the FT default, when employed on the S4 disks, decided our target MTTDL value. And for the upper bound on the stripe width, we restrict ourselves to going at most twice as wide in terms of stripe width as the default fault tolerance scheme. So the default fault tolerance schemes we evaluated were the canonical 3 replication, 6 of 9 erasure code, which means 6 data blocks and 3 parity blocks, and 10 of 14 erasure code, which means 10 data blocks and 4 parity blocks. So erasure codes are more popularly used in large clusters for durability. So I'm going to be talking about results only about the erasure codes. You can see the 3 replication results in the paper. So among the 6 disk groups, I'm going to be talking only about 2 disk groups for the purpose of evaluation right now, H4A disks and S8E disks. So for H4A disks, you can see all 3 phases of the bathtub curve clearly demarcated: infant mortality, useful life, and the wear out stage. But for S8E disks, you can only see infant mortality and part of useful life. And that's because these disks are young, they're installed late, and they're yet to see their old age. So what happens when you feed a bathtub curve from a reliability monitoring infrastructure into HeART? This is the result. So the first thing I want to point to you is that there is an existence of a black curve along with a red curve. That curve is the non-anomalous data. So after passing our regular bathtub curve through the anomaly detector, after filtering out the anomalous disks, we get the black curve. Since they are anomalous, by definition, almost always the black curve will always be on top of the red curve, if not very nearby. So the next thing I want to point out are the 2 X's, which is the change point detector marking the end of infant mortality and the start of wear out. Now, as the reliability data was periodically provided to HeART, the way we mark end of infant mortality is we look at the first 30+ day flat reliability chunk after the first 90 days. And when the reliability between those 30+ days is flat enough, according to some tunable threshold, we consider that infant mortality has ended. At that point, HeART determines a useful life failure rate for that disk group. So for H4A disks, at the end of its infant mortality, HeART determined that the useful life AFR should be 1.82%. And that 1.82% came by looking at the failure rate at the end of infancy and adding a user tunable buffer value to that AFR value at the end of infancy. By default, it's 25%, but it's configurable according to however conservative you want to be in your approach. Now, the second X to the right marks the end of useful life when the failure rate again starts going up, and we mark that useful life has ended, and now we need to re-encode the data back into the default fault tolerance scheme. So when useful life started, we re-encoded the data according to a failure rate of 1.82%, according to a low redundancy scheme, and we re-encoded back into the default fault tolerance scheme when the useful life ended. For S8E disks, we can see that only end of infancy is marked because the disks are currently in their useful life. And the heterogeneity comes from the aspect that for S8E disks, the failure rate is 2.48%, while for H4A disks, it was determined to be 1.82%. This is the heterogeneity in AFR values. So let's look at how much storage cost we were able to save. So when we employ a 6 of 9 erasure coding scheme as the default, we have to remember that a 6 of 9 scheme is pretty aggressive in the sense that it has a small storage overhead of only 1.5x. And to recap, when we say that 6 of 9 is default, we mean that the infancy and the wear out stages employ a 6 of 9 erasure coding scheme, and we have a disk group specific scheme according to the failure rate determined by HeART in the disk group's useful life. And so in this graph, I have the disk groups we evaluate on the x-axis, and on the y-axis, the disk space saved as a percentage. So for S4 disks, since that was our baseline, we never changed the redundancy scheme, and therefore we see no benefit. For H4A disks, which had a 1.82%, we could employ a 12 or 15 erasure code during useful life without compromising the target reliability. which had a lower storage overhead of 1.25x compared to 1.5x, and therefore ended up saving 16% in its useful life. Similarly, for S8E disks, we could employ a 10 of 13 erasure coding scheme and a storage overhead of 1.3x, leading to a 13% savings in useful life. Now, when you consider both the infancy and the wear-out stage, the overall lifetime benefit is between 10 and 11%. So 10 and 11% in a million odd disk cluster is a large amount. And even when we employed a default fault tolerance scheme that was aggressive as 6 of 9, we could get an overall benefit of 10 to 11%. Similarly, if we go even more aggressive by having a 10 of 14 erasure coding scheme, which has only 1.4x storage overhead, we see that H4A disks can employ a 20 of 24 code, and S8E disks can employ a 17 of 21 code, leading to a 14% and 11% useful life benefit, respectively, and an overall benefit between 8 to 9%. So in conclusion, I'd like to mention that exploiting reliability heterogeneity is very real. It has potential for large storage cost reductions. On a production data set, we observed 11 to 33% space savings. And we have developed HeART, the heterogeneity-aware redundancy tuner that actively engages with the bathtub curves as they are formed. It has a built-in anomaly and change point detector. And it suggests cheap alternate redundancy schemes that meet target reliability and reduce storage cost. That's it for my talk. I'm open for questions. Thank you.
Hi, I'm Danny Harnik from IBM. I wanted to ask about how do you expect to actually deploy such a thing? I mean, is the monitoring something that you think of as being done by the disk manufacturer on a batch, or are you doing it in your data center?
So, like I mentioned before, there is some sort of a disk health monitoring infrastructure already in place. The slight difference is you might have to monitor on the basis of a per disk group level. And if you only consider make model, there are only a handful of make models in play at any time. So in terms of the monitoring overhead, it shouldn't add much more complexity in your instrumentation to monitor.
But in terms of what should be the size of my deployment to actually have some meaningful statistics on this?
So we evaluated, so there are many statistical bounds possible to identify what disk population you require in order to be statistically confident. And so we use something called the Chernoff-Hefding bound. It's just one of the bounds out there. And according to that, for a failure rate of roughly like 3.2% AFR, you require somewhere around 4,000 disks to be confident, which doesn't seem an unreasonably large number in looking at the fact that you have hundreds of thousands of disks usually in your cluster.
And one last question. The anomaly detection, I assume, is there to allow you to actually find the 2 points, but when you actually go and then compute the reliability, do you add the risk of these anomalies, because these anomalies did happen? Actually.
Yeah, so now, no matter what redundancy scheme you are using currently, even without our optimization, there is a bad number for the number of failures that you can tolerate, right? So if you lose hundreds or thousands of disks on a particular day, then you're anyways going to have some sort of a risk at that point. So we think the right way to view redundancy tuning is separate from this anomalous failure. So these anomalous failures need to be identified, but need to be dealt with in a different way, probably in a preventive manner or by looking at other indicators that might show to you that something of this sort is about to happen. But the redundancy tuning doesn't take into account the anomalies or the spikes that occur.
Okay.
Yeah, thanks.
In the back, please.
Hi, Dean Hildebrand, Google.
In the back, please.
Hi.
Sorry. So I noticed that your workload was a backup workload, and typically a backup workload. Have you like for example, have you considered any cloud storage workload where It adds another dimension. Some disks are hot, and as opposed to a backup workload where the data may not really be accessed that often.
Good point. So unfortunately, this was the only open source data set out there. So we analyzed this. But currently, I'm in the process of analyzing other data sets of of different kinds of workloads. And I should have more results. So I am analyzing that right now.
Thank you.
So the one thing I didn't understand was you took the bathtub curve that normally applies to individual disks, and then you applied it to entire disk arrays, or at least into groups of erasure coding and how they're grouped. So how does that work over time in terms of how failures occur individually to those disks inside of the group, and then every disk is running on its own bathtub curve?
If I understand correctly, the bathtub curve in general is sort of a population statistic and not an individual disk statistic, right? So when we say burn-in period, we're talking about for example, we're talking of a population of disks being deployed and more number of disks failing initially, which is being captured by the high failure rate during the beginning. So it's not, so for an individual disk, it either is active or it fails, so it's binary. But when you take a population, it's the fraction of disks that failed that shows the high percentage during the beginning. So I believe bathtub is a population characteristic.
Yeah, but I guess my point is that you don't buy a set of disks and then stick with those disks for the entire lifetime of the data center, right? You're constantly buying new disks, and they all come with their own failure bathtub curves, right? Because the initial part is manufacturing defects that come with as you're deploying them. So I'm just trying to think about how this would apply in a real-world scenario where you're constantly individually replacing individual disks and not just swapping out entire disk arrays.
As far as the conversations that we've been having, disks are usually purchased in batches and also deployed in batches, right? And the sizes of those batches may change, but the point being that when you buy a model for the first time, that is when you'll first start chalking the bathtub curve of that disk group.
Yeah, I mean, we could talk offline.
Yeah,
That's not how things work, right? Because disks fail individually, and you can't do fail in place. You have to replace them. So you're constantly going and taking new disks to replace what is there. Otherwise, you would just end up with a bunch of dead disks in your data center.
Good point, but we'll talk offline. Sure. Yeah, thanks.
Hi, Saurabh. David from Alibaba. My question is about the replication factor, which often is overloaded. It can be chosen for availability, fault tolerance, maybe even throughput. Have you step back and consider how complicated that would be to mix these factors and whether they are at tension with each other?
Okay,
Thanks.
good point. So currently, this work focuses on replication or erasure coding from the durability perspective, not from the availability perspective. So if your hot data is initially has 3 replication or K replication for availability reasons, at some time it will get cold and you'll have a background process that eventually converts it into an erasure-coded, more storage-friendly format. And that's where this work currently comes in. So we're not talking about availability in this work, we're talking about durability.
So I have one last question, I
Yes.
think. When you have a large storage system like this, you charge for everything. You charge for the capacity, the throughput, and the IOPS. Have you considered the impact on your cost savings that the IOPS and throughput that you're going to have to use in order to do this data redistribution might eat into your savings?
Yeah, okay. So, even though I'm showing bathtub curves by age as though the disks were all deployed at the same time, and that isn't quite as true. Like, the disks are usually deployed in rolling batches. So if you consider the background jobs that happen today, like for example, you have failures and you have to do reconstructions and so on. Similarly, you could piggyback this transcoding or re-encoding job as a part of your background job, and you could do it over several weeks. It doesn't have to be sudden, because in an overall lifetime of a disk, which is several years, losing a few weeks worth of storage cost reduction when you enter useful life is probably something you can incur if you do not want to have interference on your foreground workload or something like that. You don't want to overload your system. So that could be a part of your background activities and done in a graceful manner.
All right. Well, if there's no more questions, let's thank the speaker one last time.
Thank you.